Au bâton bleu, test 1, 2, bâton bleu. Test 1, 2. Oui, je peux mettre les deux, il n'y a pas de problème. Ok. Généralement, ça se suit. Il n'y a pas de problème. Il n'y a pas de problème, je vais mettre le noir.
Hier, c'était vraiment nécessaire. Aujourd'hui, ah oui, non, c'est pas parce qu'elle était intéressée par son histoire. Non, donc, alors, je crois que c'est bon, on est déjà parti. Oui.
Je vais attendre qu'on a le Japon.
Oui, c'est comme ça. Donc, on a un produit, parce que c'est l'axe, c'est le responsable d'axe, mais après, c'est le responsable d'axe qui gère.
Bonjour, bienvenue. Merci d'être de retour. Thanks to be back. So we start the second day of presentation of the activity of the PEPR. So we start with the presentation of the axis number 5. So this is an axis devoted to the numerical revolution and how we can use it for our purposes. So there is the responsible of these axes are Guillaume Laibe and Maud Langlois. So as usual, they will give a half an hour introduction on these axes, and then the leaders of the 4 working packages will present their activities. Thank you, Guillaume.
Good morning, everybody, and welcome for this session on the morning on the numerics. So this presentation will be split in two, one from myself on high-performance computing, and another one from Maud Langlois on data analysis. So let's start with numerical modeling, and I will call this presentation Road to Exascale. So exascale with an E, not an H. So for those who are not familiar, what does this mean? Exascale, it means 10 to the 18, so 1 billion of billions, so 1 quintillion of operation per second. So since a couple of years, we have access to an unprecedented power of calculations, and as it can be obvious to see how it will be helpful for cryptography or deep learning, we'll see why it's going to be super important for planet formation and the origins of planets. Okay, so we know that we have discovered and observed a lot of extrasolar planets. Key questions is how and where do they form and in which environment? And more precisely, since a couple of years, we have constraints from meteoritic data, from direct observations, that we observe planets in young disks, and those disks are also complex systems by their morphology, by the physics they involve, and so on. So this is both a bad and a good news. Bad news because it's complex physics, so you cannot solve the problem analytically. Okay, so you have to do numerical experiments. That's it. The good news is that the systems are relatively young, so it's less constraining in terms of duration for your simulations. So it means that some of the simulations are accessible. And the key question we want to solve is how do we form those disks, how the angular momentum is transported, how can solid grow and concentrate, and what is the origin of the substructures observed in these disks, when do planets form or start to form, and how to interpret meteoritic data. Okay, so what are the challenges for numerical simulations? The first one is it's a multi-physics system. So I take you one of my favorite objects. It's HL Tori. It's a disk observed in the millimeter. So what you see here is like sand grains, like grains around a young star, organized with this kind of structures. And plethora of models have been proposed to try to interpret this observation. On the right-hand side, the two models on the left involve the magnetic fields, and the two on the right involve dust grains. So at least you have two ingredients which should be or either be considered by themselves for interplay, but you can also involve other effects such as gravity, radiation, chemistry. Necessary physics to try to understand this kind of evolution. Now, do we have to simulate only the disk? Well, answer is no. Why? Because planet formation is a byproduct of the evolution of the interstellar medium. Gravity concentrate material. So you have a multi-scale out of equilibrium system just due to the gravity. And you can see here that at very small scale, where you will form the planet, it's surrounded by an environment, and you cannot disconnect the formation of the planet to the environment. And you have a back reaction between the small scales, so the radiation generated by the stars, and their magnetic fields onto the large scale. So you have to deal with these multiple scales out of equilibrium. Okay? And finally, up to where do you have to go? So can you simulate either the disk or can you simulate just the environment? The answer is no. So it's so from now a couple of years, an idea proposed by Alessandro Morbidelli, Sébastien Charnoz, and Benoît Commerson, that already at the stage of the formation of the star, very interesting stuff appears in unusual conditions. So you want your numerical simulations to be able to simulate that. So, as a summary, why do we need exascale? Because with exascale, we have all the scales. Okay, that's it. Okay, now where is the magic? Okay, why we were not able to do this before? The magic is that, so before, we were computing on computational processing units called CPUs. The way you treat the data with the CPU is the following. You have a good processing unit, and you access the data through a system of caches organized like Russian puppets. So you have to go to these Russian puppets, get the data, compute, sort the data out, and deal with them. But this works fine up to the stage where your simulation is not dominated by the access to the data, and you are not saturated by the communication and the way you have organized the data. For exascale simulation, it's not the case, and you end up with just a mess, right? It's too expensive. Remember that 1 million CPU hours is 20,000 euros, and it's 4 tons of CO2. So if you start to run an exascale simulation with CPUs only, you end up to just involving like nuclear power plants. It's not ecologically and socially sustainable. So you want something else. And what is that? So how you deal with this traffic issue? Well, you organize. So you organize the calculation, you organize the data, and then you communicate it fastly. And this is like broadly what the principle of a GPU, graphical processing unit. So you have pre-processed the data, and then you send it up to a lot of computational units that are cadenced slower, and then are less dissipative, but you have pre-processed and organized the calculation, such as for the same computational power, you have much more efficiency. You can optimize the cost up to a theoretical factor, let's say up 10 if we are dreaming, which is very important. Just at a national level, strategical level, fine, but also in your institute. So for example, in my own institute, ENS Lyon is paying for the lab, for the CRAL, every year, 400,000 euros in terms of electricity. Okay? So if you can reduce this by a factor 10, it's important for your president and your colleagues. The other thing is that you have no choice, because this kind of architecture are very, very powerful for deep learning and all this kind of artificial intelligence, right? Where you have random operations that you can very easily spread and collect. So just you have to do it. Okay. The problem is that the equation of physics in nature, they are not random. Nature is conservative. You have a set of hyperbolic equations with some conservation, like div b should be 0, like period. So it's a technical issue. Okay? Why? Because you can take advantage of the GPUs, but it's very, very, very fine-tuning to get very, very nice efficiency. Equations of physics are complicated. The key thing we have seen is that to deal with that, you need people that are both experts in high-performance computing, so that can deal with the hardware, can understand the algorithm, and know also the physics. You have a question of how you handle the data. It's petabytes of data, right? So you have to handle the analysis, storage, reproducibility of data. You have to handle the versatility of your code. You should not, if you want to design a communitary code, it should be helpful for a lot of problems. Okay? Portability, maintenance, so it's at the stage for this kind of code of software design. And of course, we have just 7 years to do it, right? So a couple of things related to the strategical plans. So what we have to do in this PEPR? Okay, it's for France 2030, so we have to develop algorithms, modules, and codes that work, essentially. So here, these codes, they don't exist in other communities, such as aerosol, cloud, combustion. So I'm not saying that we will use this to do simulation of climate, but surely the algorithms and the knowledge we will develop and the people we will form is going to be helpful for the other communities. We have to try next generation of researchers with these 2 levels of expertise, HPC physics or astrophysics, and then we have to perennize these technical skills developed. This is a very important point. We will have engineers, and we have to perennize this expertise. Otherwise, in 7 years, we'll just have a nice instrument with nobody making it work. Okay, just before I stop, what's the strategy? Because okay, we are told we have to go now on these exascale clusters, and we have to start from scratch. So what's the strategy? How to answer quickly to a complex and unknown problem? Well, one example of what happened sadly in the last year was this. All right. So the strategy was not to put your eggs in the same basket, and so you try to maximize, to cooperate at maximum, and try different things that are complementary to be as optimal and minimize the risk. So the strategy we have chosen actually is not an improvisation, because it has been it relies on collaborations which have been initiated since 2018 with the programmes nationaux, with the Action Spécifique Numérique, with the GINEA consortium from people doing high-performance computing in France. So I will, of course, Geoffroy Lesur will speak more about that when he will present the work package 1 about this axis. But the taste of how we have organized, we have developed several codes. One is the fer de lance, let's say, is Diablo, ported by the CEA, which is ambitious code, agree with a raffinement adaptatif, like next-gen for Ramses, for example. The other one is the one which works currently, and which is performant, and which we have publications, is IDFX, developed by Geoffroy Lesur and his team in Grenoble. And one is a bit more specific, dedicated to particles and a bit of disorder, and is developed in Lyon by us, called Shamrock. Okay, so I will gonna stop there, and I leave the parole for Maud, and Geoffroy will deal now after on science and technical aspects of this HPC in his talk. Thank you very much.
So maybe we'll get the question after. Oops. I will switch to the more the data analysis axis. So this axis actually was actually brought to the PEPR a bit later than the others, and there is a numerical revolution. So from very complex calculation for the simulation, but also for the data analysis. So I will step back. What we've seen yesterday was like the challenge for the ELT, and it is a challenge from the component and the technical part we develop, but also from the data analysis, so the science data to actually get to the exoplanet signal or this signal. I will show here basically why it's important, so based on experience that we had so far, and what we will do in the PEPR will then be presented by the responsible of the work packages. So basically, so if you see at the top, for those who are not very used to high contrast data for direct detection of planets, you are in a situation where basically the light from the star leaves a huge amount of structure, and in that in these images, you actually are trying to look for a planet there, but many, well, here all are artifacts from the star. So you need means to distinguish noise, which is a structured noise, as seen on this image, to actually get to this image at the end. So you see there is a huge step that needs to be taken with very high care and require most developed technique in the algorithms we want to develop. So maybe in steps, so yesterday we talked about adaptive optics to get to the diffraction limit, and the second step is the coronagraphy to block the stellar light, but as you see there is remaining artifact, and here we have a bright companion which is barely detectable. So sometimes if we want to go fainter, it will be actually mixed with the stellar features that are present in all images. So the tools, the instruments have been designed to actually add some diversity into this image to be able to retrieve this planetary signal, for instance, here on the right image. So the step is quite huge. You go from raw image contrast 10 to the minus 4 to 10 to the minus 6. So there is a factor 100 that is actually a burden for the algorithmic part, assuming that the diversity conditions that are provided by the instrument are sufficient. So it's not a small task. So just to look at the data, so I showed the data because I think it's good to understand. So you've been shown many images of exoplanet and disks that look nice and perfect, but the first step is really on the detector, you encode this kind of images. So here you barely see a disk, which is quite bright. We want to get fainter, so you always have this pollution from the star that you need to deal with. So one step is that the instrument provides some diversity, so we actually can include some rotation around the star, which is artificial, or some spectral diversity, which you see here. And then we have time sequence with color, let's say color sequence, that adds means to disentangle speckle noise and the planet signal. Okay, so in the data, it's encoded. There is some diversity that actually helps, but then the step afterwards for the data analysis needs to be designed properly to make use of this. So I cannot switch any more slide. Something changed. Je crois que j'ai plus la main en fait. Ah, ok. Ok. It's working again. Sorry. So I showed you it's difficult. The data actually have information that could be actually used, and this is a very active field of research. So here I showed example of data analysis methods, a signal extraction for disk structure, which is also of interest for this PEPR. We are looking for exoplanet, but exoplanet are in an environment that is really interesting to study for the formation of this planet. So this is an example of disk. And from this data, this kind of data I showed before, which is polluted by the star, we want to extract the disk features. So there are many examples, and I guess the last decade has been quite rich in the processing tool, but we can go a step further. And so Loïc will actually show you how. And you see in the sequence there are many different tools that have been developed. There is still lots of work to do because we want to get to more difficult target detection. Here are some. So I focus. I'm sorry. I'm focused a little bit more on the data analysis and not on the adaptive optics and scheduling because we have nice image, nice result, and I think I wanted to really highlight that the work had started and really the PEPR will actually lead to new method and much more efficient than what has been developed so far, which is quite very interesting. So these are results from Olivier Flasser using RexPaco. So we are starting from the same images I showed you, and then we can extract a disk properly. So this is also spectroscopic data. So we have color information, and we can retrieve a total intensity. So this is compared with the old first developed technique, and this is the new technique, which actually benefit from the spectral diversity to recover, in particular, a symmetrical feature, because you have, as long as you know the physics behind the speckle behavior with wavelengths and the behavior of the object, and you can actually disentangle better and get full information, total intensity, and even spectra. So another result, which actually is very interesting, is we have means also on the polarimetric data to extract signal properly, which can be combined to the total intensity to lead to very fine study on composition by using the phase functions, and also to increase the sensitivity. So this is Abe Origae, which has been actually observed with the sphere instrument, and you see the total intensity and the polarized signal, which is actually quite stunning. There is an ANR that has been that has started on this matter, but it will really end before the PEPR will actually take over and do greater things. Also deep learning, because then it's really getting very important in the field. So there have been already work also from Olivier, and in the context of the Anne-Marie Lagrange, the ERC. So the Cobrex ERC has actually supported some development around deep learning, which we want to take further in the PEPR. Results. So why all this? Why we want to go a step further? The problem is depicted here in contrast. So we really want to push the contrast down. This is the separation from the star. This is the level of contrast. So I remind you, you want to go to the 10 to the -8 somehow. So not on this data, but as much as we can. So here you see a contrast curve from like all techniques, like standard technique already, we are pushing it down. So you see the deep PACO, which has been developed by Olivier, is fairly close to reaching the ultimate photon noise limit somehow. So it can manage to learn the feature from the speckles to actually get as deep as we can on a given data set, which has a given time of observation, basically. But there is still this gap. So here we want to go as close to the star, and this gap is really worth studying, and we really want to learn here to do better in this PEPR. Some work also from Theo Baudrito. This is a collaboration between Olivier and INRIA people trying to actually use speckle generation with diffusion in deep learning to actually reproduce the speckle I mentioned. So it's a way to learn the noise that are actually in the high contrast imaging. This is also based on the sphere instrument so far, because that's the one we have at hand, and we have quite a lot of data to learn from it as well. There is an important step so we're planning to use the ELT for pushing the contrast down. So that means we will have to observe for a long time. So in a given night, we have only a few hours or several hours, let's say, but then we want to observe the same target for several nights. And what happens, because we will look at closer objects, planet will rotate faster, and in between nights of observation, it will happen that the planet would have actually moved around its star. So if we want to recombine the images efficiently, we need to take into account the Keplerian motion of the planet around its star. So there is also specific development on the algorithm that we want to use to do this. So these are results from Jules Dalland still on a sphere data set, but you see this basically you have several epochs here, and this is the worst one. So the planet is barely detected. This is a low SNR, and then the best epoch. But if you combine the 23 epochs, you will end up by raising the SNR, and by doing so, you can also have access to better characterization. So it's detection, pushing the detection, and also enabling some finer characterization, because basically SNR drives the accuracy of any measurement you want to do, either photometry or astrometry. So in results, this work, for instance, we show the contrast curve, so the limit in sensitivity for single epochs, and if you combine them, you do gain in contrast. This is quite significant, in fact. If you can observe the same target, taking into account its rotation around its star for a long period of time, and you can recombine efficiently the data, you will end up increasing the sensitivity of the full sequence. This is critical for the ELT. For VLT, so sphere instrument, the rotation is not so significant because we are targeting planets that are quite far from their star, but if we want to go closer, then the motion becomes faster and significant. So one last point, maybe to link the other work packages. So the data are complex, so we design algorithm to tackle this problem. On the other hand, data from adaptive optics and high contrast imaging are also very variable in time. So you see, you see a sequence here. This is just the flux of the supposed exoplanet somehow, which is captured by different means and Strel ratio. But then you see, as you go in time, really your residual are varying, and this is just representing the fact that the adaptive correction is not perfect, or the observing conditions are very variable, and this also needs to be taken into account. One work package led by Eric Thiebaud is to deal with making the system, developing algorithm to make the system as stable and as optimal as possible. So it's really real-time control for adaptive optics, but unsupervised, allowing robust correction, and there will be variation at the end, but at least that's a way to actually drive the system as optimally as possible to reach the highest contrast possible. So this is, you wonder maybe on the images, this is not exoplanet, but it has been tested on the Themis telescope, which is a solar telescope and an EO system that was actually developed by the team. So you see, so I didn't have sequences, but it really, so the example here on solar adaptive optics is really clear because the observing conditions on this kind of observation are even more drastic than for the nighttime. So the result is really highlighting the capacity of the instrument, making the adaptive optics work more efficiently. So this is key for adaptive optics, and this will actually generate images which are have less contamination as we can and very more sensitive. The last part is the smart scheduling. So this would actually be presented by Julien, I think. This is the work package led by Anne-Marie. This is also key. I mentioned, so the relation between adaptive optics and observing condition is quite important. So if we really have bad turbulence condition, adaptive optics cannot really cope with the full thing. So it's important to schedule the observation at the best time, and this is really a tool and some algorithms that are developed to actually learn the condition, learn the criteria that we want to observe in, and develop a scheme to observe many targets at their best time. So I will draw some conclusion, because before we actually switch to the individual work package. So we all learn about direct detection challenge. I want to, again, really state that the observing conditions are really critical, so we can tackle this difficulty, the source of noise, by really applying deep learning technique, and also trying to drive the instrument the optimal way, and the scheduling of the observation as well in the optimal way to make the most science as possible. And last point is, I think science data is really key for co-designing the next generation of instrument. We cannot build the instrument and then do the data analysis separately. We need to go hand by hand and really have full systems that are co-designed from the start to do the best we can. Thank you very much.
Thank you, Maud and Guillaume. So before we pass to the description of the individual packages, if there are some questions, I think Guy has one.
Yes, thank you very much. We heard about artificial intelligence and adaptive optics yesterday with Damien Gratadour. Are there some bridges between these work packages you presented today and the work package of Damien?
Yes, indeed. So Damien's work package is a little more hardware somehow related, but also Eric is participating to this work package. There is also already a close link. While the task for the control in this work package are separated from the GPU tasks.
We can move the work packages, so the chair.
Okay, so now next move to the work packages, and the first speaker is Geoffroy Lesur. So please stick to your time, so we can have all coffee on the time and chat together. Thanks, Geoffroy.
I am between you and the coffee break, so I'll try to be brief. Right, so this first work package is, as introduced by Guillaume, about HPC and how we can use the latest HPC platform which are becoming available to astrophysics. So it's been named MHD at Exascale, and it's a collaboration between Université Grenoble Alpes, CEA, Université de Lyon, and the IAP in Paris. So as was already explained by Guillaume earlier, we know that we do need simulations actually to understand what we observe. There are many examples. I'm showing here 2 examples coming from various work you might find in the literature. Here, this is a disk seen from the top, which is interacting with its envelope that is falling from the right. And you can recognize spiral waves, which are actually also observed in observatories like ALMA. And here, which doesn't work, you might see, or not, yes, it works. You might see here a map showing the density of dust grains, that is millimeter-sized dust grains, which are slowly accumulating and leading to this clump, as we call them. And these clumps are actually the precursors of what we think are asteroids and comets in our own solar system. And it's been shown, for instance, that this sort of simulation predicts properties for the planetesimals, which are actually observed in our current solar system. So there's a direct link between what we understand in the physics of the systems and what we actually see. So this is the current state of the art. And as it turns out, the current facilities we have access to are evolving fast. So what is shown here is the total computing power which is installed in French facilities that are hosted by GENSI versus time, starting from 2009. And you see here, this is a log scale showing the computing power versus time. And you see that you have a progressive increase of the computing power, which is actually an exponential growth. And you might see that you have 2 curves here, one in blue, which is standard CPU clusters, that is the same architecture as the one you have on your laptop. And in green, you have what I will call later accelerated clusters, which are typically based on GPU kind of systems. And you see that this green curve was rather flat until 2018 and the Villani report about artificial intelligence, at which point it shoots up dramatically. And as you can see now, this is today, at the national level, you have a power which is accessible from accelerated machine, which is 10 times larger than what you have on the old architectures, which are a CPU-based cluster. And the next generation, that is the exascale machine, which is due in 2025 and which will be installed at CEA in Saclay. This machine will also be based on a GPU kind of architecture. So, in other words, we need to be able to use these machines because it is the future no matter what. So, as a community, we need to build tools to actually be able to exploit these new architectures. In other words, the hardware, if you wish, is in advance with our current software stack. So we need to feel that. So there is also a point about energy efficiency, which was briefly touched by Guillaume earlier today. So what is shown here is it's a plot taken from the top 500. So this is the top 200 HPC clusters in the world, and you might see the colors here, which represents the kind of architectures of each of its clusters. And you can see here in blue, you have the standard CPU clusters, and here you have the energy efficiency, that is how many mathematical operations I can do per watt of electricity. That's a very simple quantity. And of course, you see here standard CPUs, and up there you see the accelerated clusters. This dot here is the performance of Adastra, which is the latest French supercomputer, which is installed in CNRS in Montpellier. You see it's pretty high up, and you see that by jumping to accelerated cluster, you have gained by a factor of 5 to 10 in terms of energy efficiency. So that's the main reason why there is this transition. It's essentially a matter of being energy efficient. Okay, what can be done? It's been already touched. You can do very long timescale integration. I'm showing here a plot from Hugo Le Breuil, showing you several protostellar clusters which have been integrated for up to 100,000 years. This is actually pretty young. I mean, many systems we do observe are several million years. It turns out that if you jump to an exascale machine, then it will be possible to actually integrate these systems up to the age at which we observe them. That is an age where you will have clear up, for instance, the parent envelope and actually match what we observe. It will be also possible to combine multiphysics, that is couple magnetic field, radiative transfer, embedded planets, grain coagulations, and also something which is a mixture of what you will see later in this axe of 5 is the coupling to artificial intelligence, that is coupling hydrodynamics to subgrid models which are designed by artificial intelligence and which is the next move in this community. So, okay, that's the dream. So, as it turns out, there is no free lunch. And in this case, it's particularly problematic. So what is shown here is how the world is divided in HPC today. On the left here, you have the CPU world, which is known as MIMD, multiple instruction, multiple data systems. So that is typically the system you have in your laptop. So imagine you have several datas in your laptop, and you want to apply different instructions to each of your data. So what will happen is that your CPU will take each of these data and apply that particular instruction. You might even have possible asynchronous flows of instruction because you have some dependency. No problem, your CPU will handle that. That's the main reason why you can check your email, listen to this talk, and at the same time type something on Overleaf and listen to music. Different tasks at the same time, and your CPU is very well designed to do that. And it's been what's been used for the last 20 years in the HPC world because it is simple to develop for these architectures. Now, of course, at the hardware level, if you want to do all these things simultaneously, you need to have a very complex hardware which is energy inefficient. Now, in the GPU world, you have the SIMD approach where you have one single instruction for multiple data. So now you still have the same vector of data, but you are allowed to apply only one instruction. And you need to apply it to all of the data simultaneously, okay? So it's very different. You are not allowed to do this sort of branching. You are not allowed to apply different instructions. So there is no dependency, and you need to have a synchronous flows of instruction. So that is the future, as it turns out. It is efficient, but it also means that you need to completely rethink the algorithms you have been using in the past. So because of that, it's unfortunately not possible to directly use your favorite code on these accelerated machines because the algorithms needs to be modified. So you need to port code or to write them from scratch in both cases. It is typically years of development. And life is not simple. To make things worse, each manufacturer has decided to promote its own technology. So you will see crazy words on the web like CUDA, like HEAP, like SQL, like there are others. So in the end of the day, you might end up being a monkey coding all the time for all the new architectures which are popping up in the world. It's not what we want. So the solution we will be using is called performance portability. What this means is that we use abstract C++ concept to dissociate what the hardware is and what the software wants to do, okay? So this is done in a way that limits performance degradation, but that allows us to, with our resources, to actually be able to maintain one source code for all of these architectures which are coming up. So in a nutshell, how is it going to work? We are going to use 3 MHD code. Well, we're going to develop 3 MHD code, which are Diablo, Idefix, and Shamrock. There's 3 code will target accelerated machines and will be based on modern C++. Why 3? Well, it's been touched upon. It's similar to treatment against COVID, but it's also important for raw productivity because you will use different algorithms, possibly different technological choices. For robustness as well, you want to make sure that the outcome, the result, is actually valid with whatever algorithm you want to use. And you want to avoid the unmountable one code to rule them all, which is a gigantic beast of 1 million lines of code that nobody can maintain. Of course, to minimize risk, we will use existing prototypes from CA and CNRS. And these will also allow us to maximize the scientific impact, because we will be able to make actual scientific applications in the project. And that will also help in terms of hiring, as I will show later. In terms of data sharing, we will use the Galactica database, which will be disseminated across all local mesocenters. And it will simplify the reusability of the data which will have been simulated, so that you will not have to rerun your simulation to perform another set of post-treatment. And we will apply the FAIR principles, which is findability, accessibility, interoperability, and reuse. So the codes will be publicly released under open sources licenses, so that they can be used by the community. So the code prototypes has been touched upon already. Diablo, Idefix, Shamrock. Diablo is based, it's essentially the successor of Ramses, which has been used mostly in cosmological simulation. It's block-based AMR. It's based on COCO, so that's the layer between the hardware and the software. And it also participates to the PRPR NumPex. Idefix is not based on AMR, it's based on stretch curvilinear grids. It also uses COCO, so you can see that there are some common features between the two. It has already constrained transport MHD, and it is already in production in some national centers. And finally, Shamrock, it's a different algorithm based on smooth particle hydrodynamics. It's using a different performance portability library, and for the moment, it's doing hydrodynamics. So the work packages, there are 5 work packages. 4 work packages designed to code development, and 1 work package designed for data diffusion. One which will focus on radiative transfer calculation with a scientific application which will be the dust sublimation radius, that is the innermost radius where dust disappear and where we do observe time variability and an infrared excess associated to that. We will also focus on the gas-dust interaction, and in particular the formation of clumps to explain the formation of planetesimals. Magnétohydrodynamics, and that is a big chunk for Diablo. We will implement coupling to magnetic field in a way which is reliable for long-term simulation, and include non-ideal MHD effects with the idea of applying that to protostellar cloud collapse, as shown in this figure here. And finally, an isotropic diffusion, this time is moving to larger scale. This is important for the dynamics, for the ionization of the objects, and for the generation of non-thermal particle. And finally, there is this work package dedicated to Galactica, that is a diffusion of simulation data which will come out of each of these work package. So we will make sure that each of the code we will develop can talk directly to Galactica, and Galactica will be able to do a post-treatment, so that if you have a specific quantity you need in your application, then it will be possible to directly ask Galactica, please make that plot. The work plan, well, there are many deliverables. I won't go into the details here, I don't have much time. So I will just finish with the implementation. So the total budget is 1.5 million euros on 6 months. Most of the budget is dedicated to code development staff, that is postdoc with HPC background, engineers and PhD students. As it turns out, we have already started the hiring process. It turns out it is very challenging because we are in direct competition with big tech companies, because we are looking for the same profiles, but we don't have the same salaries. So just to put that in perspective, this is a recent article taken in Le Monde, showing that Tesla has put 1 billion euros on a new HPC machine to do machine learning for their cars. And of course, these guys are hiring the same profiles like crazy. So it is making our life a bit difficult, and that is why we have decided to focus mostly on postdocs with HPC background, and not directly engineers in HPC. So take-home messages: pre-exascale machines are already there. Exascale machines are coming. The first one will be deployed in Europe next year. The exploitation relies on new codes, and you need to develop them in a performance portable way. So we will bring our prototypes up to speed so that we will have tools that are reliable, well tested, not quite Nautilus, if you know what I'm talking about, and which will be dedicated for astronomy and fluid dynamics communities. We will build a national expertise on GPU and exascale challenges, mostly data movement, fault tolerance. And finally, the hiring process is already a bit challenging. So we've decided to move to a physicist with HPC background. So if you do know people who have this background, who want to dive into that, please contact me. I would be happy to have a discussion with these people. And thank you for your attention.
Thank you very much, Geoffroy. Any questions for Geoffroy? Yes?
Okay. In few words, can you explain the principle of accelerated clusters?
Of accelerated processors?
Yes, in few words, if it's possible.
In a few words, the idea is that you simplify. Inside a processor, you have several little chips. You have one chip which is dedicated to the actual arithmetic operation. So you keep that. But you also have chips which are dedicated to actually understand the instruction which is coming. You have chips which are dedicated to trying to fetch the data in memory. So what you do is that you decide you have many arithmetic units, but just one chip to do data fetching, to do instruction decoding, this sort of thing. So you become super efficient because most of the transistors are dedicated to do arithmetics. But it means that you need to think ahead your algorithm so that you don't need to have many different data fetching, many different instructions. You need to have one instruction with lots of data. So that's why it's efficient. It's because most of the transistors are actually doing maths and not doing crazy decoding or fetching memory, this sort of thing. So that's why it's efficient.
So these codes will be extremely complex. So when somebody wants to use them, it will be very hard to see what is inside and adapt it and so on. So they will be basically used as black boxes. So are you thinking about the interface, the user interface, so that a broad community is maybe able to use these codes without having to plunge into coding?
Yes. So we're starting to have some experience with that. The idea of this C++ layer is that really you have objects which you don't quite know what is behind, and you don't need to know because that's really an engineer work. But once you know how the object is defined, then you can say you have an object which is a kind of array, let's say. Then you can just talk to the object, and any physicist can do that. It's not directly the hardware, it's some abstract concept. So the only thing is to understand that you need to understand C++. That's a big step forward, I would say. But once you're there, that's fine because, okay, the objects, you don't need to know what's behind. You just need to know how to use it. And what's behind is actually very hard, but not your problem.
One final question there, and then after I'll leave the other questions for the coffee.
Yes, Geoffroy, in the private discussion yesterday, you mentioned that on the biology side, for instance, there were many people already in line to using the supercomputers with the same techniques. So this triggered the question, is that in the framework, it's not apparently present in the PEPR as it is, but is it conceivable that on the biology side, for instance, molecular complexity, that it could be other series of modeling and computing that could describe or model some form of molecular complexity?
So for the molecular complexity, I don't know, but what is sure is that we are using some of the tools which have been developed by the various communities. So for instance, the COCOS library, on which some of the prototypes I've presented are based on, are actually heavily used by various communities. So we're using recycling, if you wish, some of the tools which have been already developed by other communities who are in advanced with respect to us. Now, for the molecular complexity, I don't know. I don't know enough the algorithms which are behind that to know how it can connect to what we want to do, to be honest.
Yes, but it's just a suggestion perhaps to look more in detail, you know, in the coming years on this potential
that's a fair point.
input.
That's a fair point, yes.
Okay, we should thank Geoffroy again. And now it's Loïc Denis will present work package 5.2, Artificial Intelligence for Optimal Information Extraction from Noisy Data.
Okay, thank you for the introduction. Good morning, everyone. So, in the previous talks, you've been given the general context of exoplanet search and exoplanet characterization, and it requires to combine different kinds of techniques, observations that may be direct or indirect. And what Maud has shown you this morning is that just by improving the data processing techniques, we can gain a very significant sensitivity and be able to reach exoplanets or structures that are much fainter. So the objective of this work package is to improve the algorithms we use in order to process the data. And you are all aware of the major progress that have occurred in AI these last years. And how did the domain progress? By using more complex models, and those more complex models are typically non-linear, and they involve many parameters, and once we've defined the model, it is fitted to the data. And it has led to breakthrough in the interpretation of images by using huge models trained over massive data sets. As an illustration, I'm just showing you a model that combines image and text, and that can be used for what is called few-shot learning. That is, we give just 2 examples of a task, and then the system is able to provide an answer. So, for example, in this image, we say pandas 3, this image dogs 2, and then the system is able to infer that the object of interest here are the giraffes and provide a correct counting of the objects. So very powerful systems, but in order to use them for astronomy, in fact, we really have to design specific techniques because of the specificities of astronomy. In astronomy, and especially the search for exoplanets, we are interested in very small signals. And we've got huge perturbations, in particular in direct imaging. We've got a lot of light that comes from the star and that pollutes our measurements. And also what we want to do is to make a scientific use of the result so that we don't just want the raw result, but also information about the confidence of the systems, uncertainties about the estimations. So in order to reach this goal, we need to set up a multidisciplinary collaboration to combine observations that come from instruments, and those observations are some uncertainties, so we need to account for those uncertainties, and the idea is to combine observations coming from different instruments, observations of an object at different times, or even analyzing jointly whole archives of observation from a given instrument. And those observations will be used in order to build models that will include instruments, so the knowledge of how the instrument is working. And this requires some parameters in order to characterize the instrument. So some of the parameters are well known through calibration stages, but others need to be estimated directly from the data because of some changes between calibration and operation of the instrument. We can also have physical models of the object that we observe, like disks. And also the sources of fluctuations can be characterized through models that also depend on parameters. So all those parameters can be estimated or learned by confronting the model to the observations. So the idea is to combine physics-based modeling by including knowledge from astrophysics, the instrumentations, but also from data science, so that covers statistics, machine learning, signal processing, and inverse problems. So there are some tight links with other work packages of the PEPR, especially the measurement of the wavefront and the adaptive optics control. So in this work package, we gather a wide community of experts from astrophysics and instrumentation for astronomy, but also from the data science side. So in order to illustrate more precisely what we want to do, we want to design algorithms that can process data from instruments like high contrast imaging, direct imaging of exoplanets. So from that kind of data, we want to detect exoplanets, so to provide detection maps where we can clearly identify exoplanets. And then we want to characterize those exoplanets by estimating, for example, the spectra of the exoplanets. Another kind of problem that the data processing needs to solve is the reconstruction of structures like disks. So this is one of the images that Maud has shown before. And just so that you get a more precise view of what is going on under the hood, I will just show you very quickly the kind of model that has been used by Olivier Flasser to perform this reconstruction. So I was speaking about model and estimating parameters. So in this case, we've got some observation, that's the data V, and we want to recover a disk that is defined through a large set of parameters. And for that, we include a model of the instrument that relates the object to the measurements through M that may depend on some parameter that need to be pre-estimated or fine-tuned on the data. And then we need to measure how close our model fits the data. For this, we need a data fidelity measure from a statistical point of view. And also, because we are trying to solve an inverse problem, often we need to include some regularity constraints. So in the particular algorithm called RexPaco, what we did is that we learned a pretty intricate data fidelity term that can account for non-stationarities in the measurements, but also spatial and spectral correlation, the structures in the background that corrupt the data. So these are all those parameters that need to be learned from the data in order to better model how observations are corrupted by some fluctuations that have some structures and non-stationarities. And then we also need to add some regularity constraints. So this is a classical mathematical function used in order to promote an image that is smooth, so with a spatial gradient that is sparse, and also an image with a background that is at 0 by minimizing the L1 norm. So this is just to give you a more concrete view of the kind of approach. We will minimize a cost function that promotes a reconstruction that fits well the data in the sense of a model of the data that can capture all the fluctuations that occur in the data. So I've illustrated detection, estimation, and reconstruction problems. Also of interest are unmixing problems, where we need to separate two contributions, one from the star and one from the planet, or fusion problems, where we try to merge information coming from different instruments. And finally, a task that is really interesting is that of co-design. So the idea is that if we characterize the performance of the data processing technique, then we can give some feedback to the optical design of the instrument or the general design of the instrument in order to jointly optimize both the way we collect the data and the way we process the data. So this is something called co-design, and it can help improve the design of future generation of instruments. So our work will be organized along 4 directions. The first one is the development of fully self-supervised methods, and we'll tackle problems like deconvolution. Here you've got an illustration of blind deconvolution performed using an algorithm developed at ONERA by the team of Laurent Munier. So you can see a clear improvement in the quality of the image, and this is fully unsupervised. All the parameters of the method are estimated from the data without requiring the user to tune parameters. So that's one of the problems. We'll also consider self-supervised learning, where we try to learn complex models directly from the data. Techniques that are targeted to specific modes of imaging, like polarimetric imaging, and also models to capture complex structures present in the data. So that's the first theme. Second theme will be on spectroscopy. Spectroscopy used to better detect exoplanets using spectrum information, and also the development of techniques to extract information from radial velocimetry measurements in order to better detect, but also better analyze exoplanets using that kind of an indirect technique. Then theme 3 will cover the exploitation of archives. So either multi-epoch, so that's an illustration of what Maud has described, of combining observation separated in time in order to better detect exoplanets that are very faint. And also there will be work using machine learning and huge archives of observations in order to build very rich models of how the instrument is behaving and the kind of fluctuations that occur in the absence of exoplanet, and then be much more sensitive and be able to detect a very tiny fluctuation that is due to the presence of an exoplanet. And finally, we'll also consider the fusion of different techniques, and in particular the fusion of high contrast imaging and high angular resolution using interferometry in order to better analyze exoplanets. Okay, so to conclude, the ambition of the work package is to develop new processing techniques for astronomy and for the study of exoplanets. To reach that goal, we've got a multidisciplinary collaboration that involves different labs with the complementary expertise. We'll be funding PhD thesis and postdocs in order to cover all those subjects, and there will be benefits both for the astronomical community. All our code will be released as open source code, and also potential applications to other fields like biomedical imaging, detecting the fluorescent signal from a single molecule is tightly connected to detecting exoplanets. We try to detect a very faint signal. So the algorithms we'll develop will also benefit that kind of field of research. Thank you very much.
Thanks, Loïc, for this very nice talk and for keeping the time. One or two questions? Yes. One Jean-François and one here. And after it's going to be coffee.
It's actually a detail in your plan. I see you have many one-year postdocs. Mm-hmm. Aren't you afraid that these are not very attractive for people to apply, or is it possible to combine several one-year postdocs for one person?
Yeah. So one of the plan is to try to recruit one postdoc to stay at 2 different labs.
Okay.
So yeah, that's a partial answer to your question.
Yeah, that's much better because it's hard for people to come just for 1 year because
yes, but it can also be an extension of a work of a PhD work. So moving to a different lab and trying to extend further work done during a PhD.
Okay, thanks.
Yeah, that's a real concern. Thank you.
Thank you for this great talk. Can you say a little bit more about the fusion of data between different instruments? What is your particular approach on that?
Yes. So, well, it really depends on what kind of instrument we want to fuse. There are different strategies in order to perform the fusion. So you can perform early fusion, late fusion. So it really depends on the data at hand. Here, the idea is to try to exploit very different imaging techniques, for example, interferometry and direct imaging, in order to combine fields of view and resolutions, spectral resolution that are very different. And in order for the fusion to be useful, we need to reconstruct an information that is common to the 2 observations. So that's the way the observation technique will benefit from one another if we fit a common model to both observing techniques. So part of the information has to be common, but then yeah, it really depends on the details of the observation technique that we use.
Okay, so thanks a lot, and we can thank Loïc again. I think it's coffee break, so we should reconvene at 11. Yep.